Hello everyone, welcome to my YouTube channel. My name is Salim and today in this video I'm going to be discussing about one of the chapters in electrical motion course. So this video might be helpful for the students who want to know electrical motion course in detail. So I'm going to make a video section video from chapter 1 up to chapter 5, which is up to synchronous motion. But for now, let's proceed to chapter 1, which is electromechanical energy conversion principle. So what is electromechanical energy conversion principle? So what is the principle? Sorry about that. So electromechanical energy conversion means it's a device that converts electrical to mechanical energy and from mechanical to electrical energy. As we know, energy is neither created nor destroyed, but it can be like converted from one form to another, right? So we cannot get electrical energy by nature. Therefore, we have to convert different kinds of energy to electrical energy. That's why we're using renewable energy system. For example, solar, wind, hydro, geothermal, and so on. This kinds of from nature, for example, if we take hydro from water, we can generate electricity. That kind of process are there. So what the device that converts this mechanical energy to electrical, first, when we take hydro, the water, when it passes through the penstock and hit the turbine, that is kinetic energy. So the turbine rotates and converts this kinetic energy to mechanical energy. And then from mechanical energy, it's converted to electrical energy. The turbine and the generator is connected through the gearbox. So it's converted to electrical energy. So that kind of conversion process we're discussing right now. So this kinds of electromechanical conversion device can be categorized into three parts. The first category will be involving low energy signals, like telephone, speaker. When we speak sound, it's converting sound energy to electrical energy. The second category can be the one that consists of forces and torque. For example, when we plug our socket when we plug in to the socket, if we consider a fan, for example, when we plug into the socket, the current starts to flow through the wire and then it starts to rotate the fan. That way, electrical energy is converted to mechanical energy. That is, the force is the one that's moving the what? The fan. The third category will be continuous energy conversion devices like motor and generator, like I said, or if we consider renewable energy devices, this one is for bulky energy conversion system. If we take wind, for example, that's generating 1.5 megawatts. That is a bulky energy generation, right? That's why for that kind of conversion system, we're using the third category. So how do we convert electrical to mechanical and mechanical to electrical? What kind of things are we needing? What kind of things are we using for the conversion process? Well, there is a coupling field medium between the electrical energy and mechanical energy, which is used to convert this, which is used to process this conversion thing. This coupling field can be electrical energy as well as magnetic, electric field as well as magnetic field. However, the energy contained of the magnetic field is 25,000 times the electric field. So that means that it has higher energy content than the electric field. Therefore, when we're considering a coupling field, then we're saying magnetic field. So like I said, energy is neither created nor destroyed, right? But it can be converted from one form to another form. But when we're converting one energy to another, we cannot get the input directly at the output because there will be some kind of losses. So here you can see in energy conversion devices, it says in energy conversion devices, out of the total energy input, out of the total energy input, some energy is converted to the required form, another one is stored, and the rest is dissipated. So for example, if our input energy is, let's say it's mechanical energy. If our input is mechanical energy, then the output will be electrical energy, right? Because this one is in case of generator. The generator converts mechanical energy to electrical energy. Some energy is stored. This stored energy can be stored in magnetic field, and in mechanical system. So there are in two ways it's stored, in magnetic field and in mechanical system. And the rest is dissipated. Dissipated means it's lost, right? Lost. So out of the total input energy, some of the energy is converted to required form. If we're considering generator, then mechanical energy is the input and the electrical energy is the output. Some energy is stored, so that energy is stored in magnetic field and in mechanical system, and the rest is lost, so we cannot get the input directly at the output. So that will bring us to energy balance equation. So the energy balance equation, we have to consider all the four things: the input, the converted one, the stored, and the dissipated. So if we consider in the motor case, if we consider motor, the input will be electrical, right? The input will be electrical energy and the output will be mechanical energy. So this is the output, but we have to consider also the stored energy. Like I said, the stored energy is in magnetic field and in mechanical system. And the other one is the dissipated. For generator, like I already explained, the input will be mechanical energy, the output will be electrical energy, and there will be energy stored and there will be energy dissipated. So what does it mean dissipated? There are different kinds of losses, which I will be explaining now. Okay, so when we say the energy is dissipated, we're saying that it's lost. So there are different kinds of losses, two types of losses actually. The first one is fixed loss. So when I ask some students, they tell me that there are two kinds of losses: eddy current loss and high stresses loss. But that kind of losses are included in this field, in this category, this fixed and variable losses. So what are these fixed and variable losses? I'm going to explain it. What does it mean by fixed and variable losses? So when we're saying fixed losses does not depend on the load. This one is, it does not depend on the load, while variable losses depends on the load. That means whenever the load varies, this fixed losses does not vary, it just stays fixed. So what are these fixed losses? The first one can be core loss, and the second one can be high stress loss. Sorry if there is some kind of spelling error problem to me. So this core loss can be further divided into two. High stress loss can be also. So the core loss can be eddy current loss. Now where I already said eddy current loss, and then sorry about this. This is not high stress loss. The second one can be, sorry, let's just erase this. First one is core loss. Oh no. The second one can be mechanical loss. Sorry about that. So core loss can be further divided into eddy current loss and high stress loss, and mechanical loss can be, what are the mechanical loss? Friction and windage loss. So friction and windage losses, the mechanical loss. Eddy current losses, the resistive or the heating loss and the core of the transformer. High stresses losses is just the reverse of magnetizing or magnetic field. Mechanical loss means friction and windage loss. Friction and windage loss means it is a loss that occurs due to the friction at the bearing and the brushes. Whenever there is some kind of friction at the bearing and brushes, that loss is called friction loss. Windage loss is a loss that occurs due to the surrounding air in the rotor. Whenever there is a friction between the surrounding air and the rotor, that loss is called windage loss. So that's the difference between these two. Variable loss can be copper loss or ohmic loss. They say copper loss, sometimes they say ohmic loss. Copper loss and ohmic loss. So this one is dependent on the load. So whenever the load varies, load is always variable. Like whenever it increases, sometimes it increases, sometimes it reduces. So whenever that load varies, then this losses, copper and ohmic loss also varies. So now that we've already discussed about these losses, let's proceed to the next one. So like I said, total loss, this one is dissipated loss, right? The total loss that is dissipated, it can be ohmic loss, which is variable loss. It can be core loss, magnetic core loss, which is eddy current and hysteresis loss. And it can be mechanical loss, which is friction and windage loss. So, so this one is the input energy. When we consider if we consider the motor, in motor case, the input is electrical, right? The output is mechanical. So the energy stored, like I already explained in the previous slides, the energy stored can be stored in magnetic field and it can be stored in mechanical system. So this one is WEAS, means energy stored in magnetic field, and WMS means energy stored in mechanical system plus the losses. So when we group the appropriate terms together, the electrical input minus the ohmic loss, which is the variable loss, will be the output, mechanical output, plus the energy stored in mechanical system, plus the losses. So we cannot obtain only the output, but we have to also consider the losses plus the stored energy, and also the coupling field. So when we write this, so omega electrical, it can be omega electrical is equal to omega mechanical plus omega field, right? So this omega field, and not omega, I mean energy field energy, sorry. So this one is electrical input. So when we say electrical energy, we're considering the input minus the losses. When we say mechanical energy, we're considering the output plus the stored energy plus the energy lost. When we say field energy, we're considering the energy stored plus the losses. So this is in the next slide. We're going to see further. So like let's just erase this part and then let's discuss the next one. I hope it's not boring though. So like I already stated here, so the electrical energy, total electrical energy, mechanical energy, and field energy. When we say mechanical, we are saying output plus stored plus the losses, and where we say field, the field stored and the field losses. These are the energy balance equation. So here, when we see the electrical system and mechanical system, we can convert this one to mechanical system or mechanical to electrical. In order to convert to process that kind of conversion, we need a coupling field. Like I said, this coupling field can be magnetic field plus electric field, but electric field has lower energy content, so we're considering magnetic field mostly. There will be losses, like I already said, there will be some kind of resistive loss here through the current, there will be voltage drop through the current. So in this case here, you can see that in case of transformer, the resistive winding resistance is quite small. Therefore, the voltage might be equal to the generated EMF. However, in this case, the resistance is not smaller. Therefore, there will be some kind of voltage drop across the I. Therefore, the V will not be equal with the generated EMF. So in this case, when we're saying input energy, we're saying WPI, we're considering voltage times current through the time dt. So this is the input energy. While the loss can be I square R, right? I square R. This one is the ohmic loss. This one is ohmic loss. and this one is the omiclos. So let's see on the next slide. We can see next slide. So here you can see that omega input energy can be Vt, which is at the time of dt, the voltage times the current times IDT. However, when we are considering electrical total electrical input means electrical minus the ohmic loss, right? Ohmic loss. Therefore, this losses. So here, the input energy electrical minus the losses. I've already stated that V is not equal to E because there will be some kind of drop across the current and across the resistance. So there will be, this one is the ohmic loss. So Vt minus IR will be when we just collect the things. And then Vt minus IR can be E. Therefore, so Vt minus IR can be E. Therefore, there will be some kind of voltage drop across the resistance and the current. Therefore, the EMF can be Vt minus IR. So instead of omega electrical, we can write EIDT. This one is the energy balance equation, right? So instead of writing omega, total electrical energy, we can write EIDT. Okay, next slide. So like I said, there has to be some kind of coupling field between the electrical energy and mechanical energy in order to process the conversion, in order to make some kind of conversion between the electrical and mechanical system, right? So this coupling field is a link between the mechanical and electrical system. And what this coupling field does is that first it has to act, or it has to react with either electrical or mechanical system in order to do this kind of conversion system. So what does it do? First, if we consider in motor case, like I said, it converts electrical to mechanical system, right? So this coupling field, first, it interacts with the electrical, with the input one. So after it interacts with the electrical system, it absorbs electrical energy. This electrical energy can be proportional to current and voltage. So when we are saying electrical energy, we're considering voltage and current. When we're saying mechanical system, we're considering torque and speed or angular speed or velocity, right? So first, what coupling field does is that it reacts with the electric system in case of motor, and then it absorbs electrical energy, which is proportional to voltage and current, and then it delivers and converts this electrical energy into mechanical energy, which is proportional to torque and angular speed. But however, if the output is electrical, that means in case of generator converts mechanical energy to electrical energy. So what this coupling field makes is that first it reacts with the input, which is the input is mechanical system. Therefore, it reacts with the mechanical system in order to absorb mechanical energy, which is proportional to torque and speed, and then it converts and delivers electrical energy, which is proportional to voltage and current, and then it brings out the electrical system. So this voltage and torque are the mechanical coupling terms. Therefore, from this we can conclude that the reaction of coupling field on the electrical and mechanical system is quite fundamental for the conversion process. So without this coupling field, without this magnetic field, we cannot do any types of conversion system. So that's all about today's video. On the next video, I'm going to be discussing about the basic electromagnetic relation, about the electromagnetic density, force, and so on. And these are the basics, but later on, we're going to discuss about types of magnetic system, like single excited, double excited, and then we're going to finish this chapter with single excited and double excited. So I hope you like this video. I hope you get some kind of understanding about what kind of how we can convert electrical to mechanical and mechanical to electrical. So if you want more of this kind of video, hope you like this video and subscribe. Also comment if you want me to redo this video in Amharic. Also, the two languages that I speak is Amharic and English. So if you want it in Amharic, you can also comment down below, and don't forget to hit that like button. Thank you for this. Thank you for taking your time to listen to this video.